Hey College Algebra, what we're going to do in this lesson is 4.2 and 4.3. Hopefully it won't be too long, but we're going to cover exponential functions and some stuff about logarithmic functions. Before we get into exponential functions, here are some properties of exponentials that we should know by now from previous math courses that we've been in, but we will use these exponential properties to help manipulate equations and other sorts of things. So you also have this list right here on your final exam and also on your next test. So don't necessarily worry about memorizing them, just know how to use these. Okay, I'm not going to go over them individually, but if you need me to in class, I will. Alright, so here are some additional properties of exponents. The main one that I want to go over in this list right here is B. The one that I have listed as B. This is going to help us a lot in solving our exponential equations in this section. So let's look at it real quick. It just simply states that if we have an equation a to the b equals a to the c, then b equals c. So that's how we're going to end up solving for our x values in our exponential equations. Okay, real quick in this one, we're going to figure out each of these values for this function. So f of x equals 4 to the x. Just replace your x value with what we are given in each of these parentheses. So 4 to the negative 2. Well, by hand, we can use our exponential properties, and this is the same thing as saying 1 over 4 squared. And 4 squared is 16, so 1 over 16 is our solution. And then for f of 5, so 4 to the 5th, that there is 1024. For something that has a fractional power, let's solve this one by hand too. We're going to say, just remember this right here, that if we have a fractional power for, let's see, a to the, say, m over n, that is equal to the same thing as the nth root of a to the m. So that's what I'm going to do, is rearrange this. 4 to the 2/3 is the same thing as the cube root of 4 squared. And the cube root of 4 squared is the cube root of 16. And then that can be reduced because we should know that 2 times 8 is 16. And we can take the cube root of 8. So the cube root of 8 is 2. So we can take that out of the cube root and say 2 times the cube root of 2. That is our solution for this one. Now, whenever we have fractional powers, the only thing I want you to do here is plug it into your calculator and give me a good approximation. So 4 to the 2.5, that's equal to, my calculator says 19.698. And there you go. Alright, so an exponential function is going to look like this. F of x equals a to the x. And what we're going to say, call a is our base of our exponential function. So you may hear me whenever we go to exponential equations, you'll hear me say equating the bases. Well, And that's the reason why, is because we're getting our bases to be equal to each other, and A here in this case is our base. Here are some graphs of several typical exponential functions, and there are some properties right here below. The domain and range here, the domain for a function of this form, a to the x, is always going to be all real numbers. And then the range of this function, because there is an asymptote here along the x-axis, we're never going to go below the x-axis. We're going to be approaching that value of y equals 0 in all of these functions. So our range is going to be from 0 to infinity, because we go from this point up. And then a little bit about this function. If your value of a is less than 1, then, or sorry, not less than, greater than 1, we have what is called an increasing exponential function. So we have these sorts of graphs that you see here. And then also when a is between 0 and 1, so something like this, a fraction, we have a decreasing exponential function. So it's flipped across the x-axis and it looks like this. One of those graphs there. And then, like I stated, this last one, in every case of what these exponential functions, the x-axis is the horizontal asymptote. Characteristics of graphs, they're always going to have these 3 points. You can rely on these points right here. So for our function f of x equals a to the x, -1 is going to be, our y value is going to be 1 over whatever our a value is. And then we're also always going to have this point right here, 1, 0. And then also 1a. And then we've already stated this right here in the previous slide, and this 2, and this 2. So we should be good on graphing these exponential equations. So let's do that real quick. So here is an example of graphing an exponential function. What I have graphed already here is the function y equals 3 to the x. And so what I'm asking us to graph is this right here. And if you remember from all of our transformations of graphs, when we put a negative in front of our function, we get a reflection across the x-axis. So what this is going to look like is this right here. Going to have that, have these points here, 1/3, 0, -1, and 1, 3. So graphing that, we get this function here. Okay? So a reflection across the x-axis of the 3 to the x function. So here we're going to, again, this graph is the function y equals 3 to the x. And again, we're going to be using our transformations to help us in producing the graph of f of x here. And what this right here causes is a horizontal translation to the left 2 units, and this right here causes a vertical translation down 2 units. So what we're going to do here is I'm going to go ahead, our vertical translation causes our horizontal asymptote to go to this line right here, -2, instead of our x-axis at 0, because we're moving everything down 2 units. And then I'm going to graph the points, or plot the points that are here. So 1/3, 0, 1, and 1, 3. I'm going to move those points over 2 units to the left. So here, here, and here. Oh, and then down. So move all of those down 2 units. So graph those points. And then draw your smooth curve through those points. Like that. And we are done graphing this exponential function. Okay, so the next thing I'm going to show you is how to solve an exponential equation of this form right here. We'll later get into solving exponential equations using logarithms to help us in solving them, but this one right here does not require that. What we are going to be using is the fact that if we have a to the b equals a to the c, then b equals c. Well, so for this equation right here, what we're going to do is make our bases the same. And 5 to the x is going to stay the same, but we can, for this side of the equation, we can make 1 over 25 into 1 over 5 to the third. Or we can say that is the same thing as 5 to the negative third. And then we're almost there. So 5 to the negative third and 5 to the x, if those are equal to each other, then just like this says, b equals c. So x equals -3. And we're done solving that equation. Let's do another one. Alright, so this exponential equation, we're going to do something similar like we did in the previous one. 9 is a multiple of 3, so change that base to 3 squared, because 3 squared is equal to 9, and then keep everything else the same. Now whenever we raise an exponent to an exponent like we have here in this case, you have an exponent raised to another exponent. Remember, use your exponential properties, and those two exponents multiply. So we have 3 to the 2x minus 6. And then now we can equate our exponents. You can say x plus 1 is equal to 2x minus 6 because of the property that I've already shown you in the previous one. When we get the bases to be the same, we can go ahead and set the exponents equal to each other. Now, solve for x. So we get x is equal to 7. And we are done in this case. Another thing that we need to look at in this section is the compounding interest formula. And you will have this on a formula sheet, so don't worry about that too much. But what you do need to remember is what each of these letters stand for. And A is just simply the amount total you have in your account after so many years. And then P right here stands for principal, and that is the initial amount that is being put into the account. And then R is the rate in which the interest is accruing. And then N right here is known as the compounding. It's the number of times per year your money is being compounded. And that N happens again up here. And then the letter T stands for time. So T is after so many years you have that money in that account. Okay, it'll state that in all your problems. So let's look at one. So we have here, it says suppose 2,500 is deposited in an account paying 6% per year, compounded semi-annually, so that means twice per year. And we want to find the amount in the account after 10 years with no withdrawals. Okay, so this money is just sitting in this account, accruing interest 6%, and it's being compounded semi-annually, which I underline it's twice per year. So take this formula and replace all the values with the numbers we have. So A equals our principal amount, which is the 2,500, and then R is our 6%, but change it into decimal. 6% is 0.06, and N twice per year, so 2. And then T is 10, and then again times N, which is 2. So that there, plug into your calculator and give me a good approximation. Please do not do this in these problems. Calculate this and then round, and then take that rounded number and raise it to this power, and then round again, and then multiply it by this number. You get a huge rounding error when you do that. So what I say is just plug it into your calculator all at once and make sure you put it in there right, and then give me the approximate answer for that. So when I did that, this is what I got. I got 4,515 and 28 cents. So that is the amount that we have in the account after 10 years. Then in this problem, it asks us how much interest is earned over the 10-year period. Well, after 10 years, what we do here in this case is take our amount that we accrued after 10 years, the 4,015.28, and subtract our initial amount from it, so the 2,500. And that is going to give us the interest earned over the 10-year period. So 2,015 and 28 cents. And that's it for that equation. Now, continuous compounding looks like this. We have A equals PE to the RT. I often call this the PERT formula, PERT. So that's a good way to remember it, but like I said with the previous one, you don't necessarily have to remember it, you just need to know how to use this. And P again stands for principal, R rate, and T for time. And E is a number. It's a real number, so that is actually in your calculator, and if you don't know where it's at, I will show you. So we have a problem here. It says suppose 8,000 is deposited in an account paying 5% interest compounding continuously for 6 years. So in this one, what we're going to do is write it. If it says compounded continuously, we're going to be using that PERT formula. So A equals PE to the RT. P, our initial amount, is $8,000. E, and then R is that 5%. and then t is 6 years. So for the exponent here, we have 0.05 times 6. And plug this all into your calculator, and what you should equal, let's see, it should equal this right here, 10,308.63 cents. And that is that problem. So here's our portion on logarithmic functions. We're going to look at logarithmic equations and their functions and some properties. So in the previous section, the reason that I put these two sections together is because logarithmic functions go along with exponential functions because they are the inverse of exponential functions. So let's look at this. It says the equation defining the inverse of a function is found by interchanging x and y. And the equation that defines the function, starting with y equals a to x, and we interchange x and y, we end up with this right here, x equals a to the y. And this is the reason we've come up with logarithmic functions. Because after interchanging x and y, we want to solve for y and get our inverse function in terms of x. So have is the logarithmic function. So this right here becomes y equals log base a of x. And that's how we get our logarithmic function. So this definition of what a logarithm is very important, and it's going to help us in solving many exponential equations. So remember that y equals log base a. This is our base. Remember, this is our base in our exponential function. So our base goes down as a little sub number. So y equals log a of x if and only if x is equal to a to the y. So a lot of our equations we're going to take from this form and then change to this form over here. So remember this definition of a logarithm. It says complete the missing equivalent forms in this table. So what this is asking us to do is use that definition of our logarithm. So y equals log base a of x, and that means a to the y is equal to x, or the other way around, we can rearrange that too. Okay, so we have the exponential form 3 to the 4th equals 81, and we're asked to change it into its logarithmic form. So 3 is our base, so that's going to be our base of our logarithm. And then 4 is the power, so that's our y. And then x is 81. So we get 4 equals log base 3 of 81. And that is the logarithmic form. Now we're asked to change the logarithmic form to the exponential form. So doing that, remember this is our base, and this is going to be our x, and that's going to be our y. So we're going to say 1/2 to the -3rd equals 8. And you can plug these into your calculator to check to see if you have it in the correct way. If we plug in 1/2 to the negative third, we are going to get the solution 8. Okay, the next one, again, we're asked to change this exponential form into the logarithmic form. So our base is here, 10. So we're going to get log base 10 of 1,000 equals 3. So now let's do this next one. Log base 5 of 1 over 125 equals negative 3. Let's change that into its exponential form. So we're going to say 5 to the negative 3 equals 1 over 125. Okay, let's do this a couple more times just so you can see this. 12 to the first equals 12. So log base 12 of 12 is equal to 1. And then here we have log base 6 of 1 equals 0. That means 6 to the 0 equals 1. So those, changing it to its equivalent form will come in handy here also. So let's remember that y equals log base a of x is the same thing as a to the y equals x. Alright, so to solve for our x values in each of these, let's change it to its equivalent form. So we get our base here is x, so we have x to the negative 2 equals 16 over 9. Alright, to get rid of this negative power that we have, let's raise this and this side to the negative 1. That's going to get rid of that. Get x squared, because these exponents here multiplied each other, is equal to 9 over 16. And then x squared equals 9 over 16 gives us the solution x equals 3 over 4, or 3/4. Here, whenever we take the square root of both sides, we're not going to worry about the negative side of the solution, because our base is never going to be a negative value in a logarithm. So let's keep it positive. Now, part B, do the same thing. Change it to its exponential form. So take our base, 16, raise it to the 3/4, and that is what our x value is going to equal. So take this, you can plug away into your calculator, 16 to the 3/4 power. You're going to get it, x equals 8. Now in this last one, again, we're going to change this to its equivalent form, exponential form that is. We're going to say 36 raised to the x equals square root of 6. And now we have an exponential equation like we solved in the previous section that we looked at. So change this into base 6, so 6 squared x, and then remember square root is the same thing as 1/2 power. So this here is equal to 6 to the 2x equals 6 to the 1/2 Now set our exponents equal to each other. 2x equals 1/2. And solve for x. Our x is going to be equal to 1. And we are done. Oh, sorry. No. It's equal to 1/4. Now we're done. Alright, this is the logarithmic function. F of x equals log base a of x. And we're going to look at some properties of it. Now, an exponential function, let's compare it to what we've looked at previously. We've seen that the graphs look like this. We have a horizontal asymptote at the x-axis, but our logarithmic function, since it's the inverse, we should have a vertical asymptote at the y-axis. So this blue line is the inverse function of our y equals 2 to the x. So it reflects across all inverse functions. They reflect each other across the line of y equals x. So that's another way of looking at it. So taking a little closer look at points that happen on each of these graphs, let's look at that. So if you notice that here are x values in our function, y equals 2 to the x, and these are all of our y values for them. If we switch all of those x and y values, that is what we have for over here for our logarithmic function. And that's what I've told y'all inverses are. It's all the x and y values are switched. So that's how we're going to end up graphing our functions too, is we can find the values of the x and y values of the equivalent exponential form of the equation and just switch them all, switch all the x and y values and plot these points on the graph to make our logarithmic function, the graph of our logarithmic function. So here are some characteristics, and the main ones that I want you to take a look at are number 1 and then number 2. If we compare it back to the function y equals a to the x, the characteristics from that graph, remember, our points were pretty much the same thing except they were interchanged with each other for this a to the x function. So that's how you're going to graph the logarithmic function is, like I said, use the equivalent form of its exponential form. Okay, and then this right here, if we know that we have our value of a is greater than 1, then it's an increasing logarithmic function. And then if that value of a is between 0 and 1, then we have a decreasing exponential function. And like we said before, the y-axis now is the vertical asymptote for this logarithmic function. And so that changes our domain. Our domain is now going to be from 0 to infinity, and the range is going to be all real numbers. So let's graph this exponential function real quick. I already have graphed for you here the logarithm. I already have graphed log base 2 of x. And what I want you to see is that the transformations apply here also. So we have minus 3 on our x value, and then or subtracting or adding 2 to our entire function. So to get this graph, we're going to take the one that we have graphed already and then shift it 3 units to the left and then up 2 units. So we're going to take these points here that -1/2 and 1 0, and then let's see, 2 1. Going to take all three of those points and move them over and then up. So over left, or take them 3 units to the left, which is this right here, and this, and here. And then take those same points and go up 2 units. So 1, 2, here. And then draw a smooth curve through those points. I didn't make my graph big enough, but it would look something like this. Remember, there's a vertical asymptote right there. And there you go. There is the graph of our function, log base 2 of x minus 3 plus 2. All right, so here are some logarithm properties that are compared back to its exponential properties because of the equivalency that these two have to each other. First one, log base a of 1 is always going to be equal to 0. So it doesn't matter what base it is. If we have 1 inside of our logarithm, that logarithm is equal to 0. And then if we have our base is the same as what is inside our logarithm, our value is always going to be equal to 1. And then these two properties that you see here and over here are known as the inverse properties of logarithms and exponential functions. We'll look at those more in the next section. And then we have these next 3 properties. These next 3 properties are going to be used in expanding and condensing logarithmic expressions, which are going to be the next few examples that I show you. So this is the condensed form of the logarithm, and this is the expanded form. So if we're asked to expand a logarithm that has 2 values inside the logarithm that are being multiplied, we expand it just like this with a plus sign in between the 2 of them. If 2 values are being divided inside our logarithm, this is our expanded form with a minus sign in between of them. And then the last one, what this one does, it takes our value of r, that is our exponent, and places it in front of our logarithm. And that's the expanded form. So take r, put it in front of our log, and we get this form right here. And this right here is also going to be used quite a bit in helping us solve logarithm and exponential equations too. So let's rewrite these expressions in the logarithmic form. Now, I'm not going to leave you all by yourself on the final exam or the next exam that you have. You will be given those logarithm and exponential properties to help you in figuring out how to rewrite expressions. So, how to rewrite this expression, use that product property that we talked about because these are being multiplied. So, the expanded form of this is going to be log base 7 of 8 plus log base 7 of 6. And that's how you expand it. Same way with this one, these are being divided. So it's kind of the same way. So log base 6 of our numerator minus log base 6 of what's in the denominator, 5. Okay, on this one, let me do one thing. Before we take a look at how to, not condense, but expand this form of a logarithm. The cube root of 9 is saying the same thing as 9 to the 1/3 power. So we're going to use that power rule and take our power we have and place it in front of our logarithm. So 1/3, not 1/2, 1/3 log 2 of 9. And we are done with that one. So now in this one, it gets quite a bit more complicated. So I'm going to do it in steps, and that's how I suggest you do it. If we have anything being divided, let's expand that portion of the logarithm first. So log base b of our numerator, rs squared t, minus log of our denominator. So u cubed v to the 5. Now expand these even further. So use your product property, and you're going to have log base b of r plus log base b of s squared plus log base b of t. And that's going to be minus, and then we're going to put this in parentheses because we're subtracting everything that comes from the expanded form of this. Log base b, again, use that product property, base b of u to the 3rd plus log base b of v to the 5. Now, the last step in expanding any expression is to take all powers that we have and place them in front of our logarithms. So log base b of r stays the same. Then we're going to put the 2 in front of our logarithm. So 2 log base b of s plus log base b of t. Then minus, I'm going to distribute this negative sign along with placing the exponents in front of the logarithms. So minus 3 log base b of u minus log base b, oh, I forgot to put that 5 in front. Log base b of v. And now we're finally done expanding this. Okay, in this one we're going to condense our expression. So go from the expanded form to the condensed form. So across the equal sign, instead of going from the left and making it into the right side of that logarithm property, we're going to go from the right side to the left side. We're going to condense all of our expressions. All of these logarithms in this first example have base 4, and it has to have the same base in order for us to condense our expression. And let's do this. We have log base 4 of x minus log base 4 of y. So our two values inside our logarithm, whenever we have a minus sign in between, we're going to divide these two numbers. So log base 4 of x over y plus log base 4 of z. And then, since we have an addition sign here, these two values inside our logarithm are going to multiply. So we get log base 4 of xz over y. Now on this next one, take 4 first, and this is the thing that we do first. We get rid of the numbers that are in front of our logarithm by placing them as the exponent on what is inside our logarithm. So we say log base b of r to the 4th minus log base b of s to the 5th. Now since these two logarithms are being subtracted, the two things inside our logarithms are going to be divided. So log base b of r to the 4 over s to the 5th. And we're done. Okay, let's do the same thing with part C. First, get rid of the numbers by placing them as exponents. So we get log base a of x to the 1/3 plus log base a of y to the 2/3 minus log base a of x, y. And that is going to be, I'm going to do this addition and subtraction thing at the same time. And this just means, okay, inside my logarithm, like this one up here, this value and this value, since they're being added, they're going to be in my numerator. And then this right here is going to be in my denominator. That's another way you can look at these. So condense it down to one logarithm. It's x to the 1/3, y to the 2/3, and x, y. Alright, that's how you condense that expression. You can go a little bit further actually on this one, and in reducing the values of this inside the logarithm. But I don't have enough room, so if you want to know how to reduce that even further, let me know, and I will do that for you. Okay, some people mistake this quite a bit, so I'll put this little caution thing in here. So there is no way to rewrite the logarithm of a sum or difference. So something like this right here, there is no way to rewrite that. There's no condensed form or expanded form of a logarithm that has x plus something or minus something inside the logarithm. Whenever you have addition or subtraction inside there, it's just a situation where it's just one term, x plus something and x minus something. That is just all one term. Okay, let's use this and our properties. Choose that this fact right here is written up for us. It says log base 10 of 7 is equal to this decimal number, and we're asked to find each of these logarithms. So what we're going to do is say, using this fact up here, we have log base 10 of 7. We should have, or should know, that 49 is saying the same thing as 7 squared. And take our exponent and place it in front of our log. So 2 log base 10 of 7. Now we know what log base 10 of 7 is equal to. It's this right here. And 2 times that is, let's see, 1.69. 0.02. And there you go. Now on this next one, 7 times 10 will give us 70. So break that apart. And use our exponential property to expand this. Log base 10 of 7 and plus log base 10 of 10. Now, remember what I said about if our base and what's inside our logarithm are the same, then our logarithm there is equal to 1. So we have log base 10 of 7, that is 0.8451, and then 1. So this is equal to 1.8451. And we're done. Okay, so like I've told you when listing all of those logarithmic properties and exponential properties out in one of those slides, this right here and this right here we will look into further in the next couple of sections, but these are our inverse properties. And we'll be using those to help us in figuring out solutions to our logarithmic and exponential equations. But that is all I have for you, so I will see you in class. Goodbye, everybody.